Very good then. We are alive with the 62nd episode of Space Rocks Uplink. It's a new year. There are new things to talk about, and well, there is no better person in the universe to speak to about those things than Mark McCorkin. Mark, what a pleasure to see you. Is it too late in the year now to still be saying Happy New Year, or what? Am I one of those people?
Definitely. No, I was going to exactly say same thing. You know, we're so in tune. We're on the same wavelength because we haven't done an uplink episode this year. So why not? First one, even though it's the 26th, I think, of January. Happy New Year, Alex.
Happy New Year, Mark. It's really nice to see you again. And, while we're doing a bit of a festive throwback, I have to say it wasn't New Year's Day, but actually Christmas Day. That was pretty special for a lot of people, observers, people involved with jwst around the world, including myself, when I got a very special FaceTime from you down in Kourou. That must feel like simultaneously like that just happened and like 5 years ago, given how much has happened since.
Well, look, it was a great pleasure to actually find that there was wireless connection and internet connection at the launch site, 5 kilometers away where we were in French Guiana. And who better person to share a little bit of that history with? I called my family as well, and they were all like, "We're watching on the TV. It's better on the TV." But yes, it was a privilege, a surprise, actually. I hadn't anticipated being there, and because it got moved over Christmas, there were a lot of people who were due to go down to French Guiana weren't available to go. They were at home for Christmas. So very much at the last minute, I got the chance to go down there, and I'm very happy I did, of course. I mean, what a moment. I was... was it going to be emotional? Wasn't it? Well, it was, and it was very emotional when the Ariane 5 lifted off, and that those decades of work by tens of thousands of people suddenly firing into the sky where it's always meant to be. And it's been so many years when it hasn't been there, but now it is.
Yeah, now, and certainly not taken for granted. But certainly, I guess it hasn't ceased to completely, I think, captivate people's imaginations around the world. I suppose that's kind of for people that might be joining us for the very first time. The whole purpose of Space Rocks is to cross-pollinate and to, I guess, extol the excitement, the reasons for so much of exploration. But, sometimes things can get lost in the headlines. I'm so pleased to see that, rightly so, the Webb telescope has actually penetrated the headlines, and I think it's continued to generate fascinating stories before the science has even begun, right?
Yeah, I think what was done very well by everybody involved, the scientists, the engineers, the technicians, and the communications team, was to lay out how complicated this thing was. In some ways, the risks were high and they were obvious, and I think that can draw people in because they want to see, well, is this going to work? Is that going to work? And this very complicated procedure of taking this chrysalis, if you like, with a butterfly folded up inside and then letting it blossom into space, getting that sun shield pulled out, which was the size of a tennis court, incredibly complicated structure with pulleys and motors and cables and a very floppy sun shield itself, very thin material which had to be pulled out to be tensioned with these 5 layers. The secondary mirror folding over the top into place. The primary mirror itself unfolding, and all of the other bits and pieces. I think that kind of tension with each step has been well illustrated, but also well described by many people. What it is that each part is, what's it there for? Why do we have this? Why do we have a sun shield? Why do we have 18 segments of gold-coated beryllium? And I think people have really engaged with that. It's not just it will take great pictures. I think people have understood that this is a complicated endeavor. Again, the result of decades of work by thousands of people. And they can watch it in real time come alive. And I think that's something which can cause great engagement.
Indeed. Well, I mean, conveying the human factor, things as simple as someone like yourself, just saying what it feels like. I guess these are things that are important to beyond the engineering, the science. It's real human beings behind it all. And so we have 2 more humans joining us this evening who are going to be telling us a little bit about what Webb is going to do beyond what was, I'll say, initially obvious to me. Tell us about who's going to be joining us in just a couple of minutes' time.
Indeed. So the the role that I play in the James Webb Space Telescope is a member of what's called the Science Working Group, which is a group of about 20 people who've been monitoring the science and the building of the instruments and the oversight of the whole observatory for almost 20 years. And so I play the role of an interdisciplinary scientist. I'm not building any of the instruments, I'm not building the observatory, but kind of responsible in a sense for looking that this machine can do the kind of science which I'm interested in, the formation of stars and planets. So our first guest this evening is Heidi Hammel, who is another interdisciplinary scientist on JWST Science Working Group, and her responsibility is solar system objects. So stuff very close by to us, the planets in our own solar system. Not all of them, as we'll ask Heidi. Why can't we, for example, look at Venus? Why can't we look at Mercury? We can't. But there's much else that we can look at, and there's lots of exciting things to be done in our own solar system. And Heidi is the Vice President for Science at the Association of Universities for Research in Astronomy. That's an organization which oversees a number of research infrastructures, including the Space Telescope Science Institute, which is where JWST is run from. So she's kind of got a double role. She's a member of the Science Working Group and in some sense oversees the operations from the position in Aura. And our other guest is Hannah Wakeford. And Hannah is somebody who has been studying exoplanets, so planets around other stars, not ones in our own solar system, but more distant planets. And she actually got her PhD at the University of Exeter. She arrived shortly after I left to join ESA in 2009. And she's been a postdoc in the US at Goddard Space Flight Center, where JWST effectively was managed. That was the core of the mission. And at the Space Telescope Science Institute, which is where it's now being operated. And now she's a lecturer at the University of Bristol in the UK. So she's very closely involved in the science of exoplanets. Heidi's involved in the science of planets. Of course, there's such an overlap between those that I hope we can talk to both of our guests this evening and find out what they can learn from each other, where JWST again, can be more than the sum of the parts.
Indeed. Well, we're going to bring them in now and just see what they have to say about what I have to say is this is a moment, isn't it, Mark? This is an incredible moment for discovery that we're just on the precipice of. And Heidi and Hannah, what a pleasure to have you. Are you receiving?
Yes, yeah. Thank you.
Fantastic. Well,
thank you both.
Thank you so much for joining us. And it's such a pleasure to have you here. As I was just remarking with Mark just a couple of minutes ago, what an exciting time, even as an observer on the sidelines. I mean, it has been a dramatic few weeks. And, what I'm really relieved to say is a story that has persisted in the headlines. It's made it outside of, what can sometimes feel like a bubble, I guess, because what Webb represents, I think, is just so universally appealing. The simple question, the oldest question, maybe, what's out there? Now, I have to kind of put you on the spot here, though, Heidi, because, I'll be honest, when I first read about JWST, I thought it just looked at stars and galaxies, and here we are talking about planets. And I kind of figure you're probably a good person to put me right.
Sure. I mean, of course, the initial concept of JWST, when it was formulated 30 years ago, was really a focus on the very first galaxies, perhaps even the very first stars that formed in the universe. But the tool that needed to be crafted to do those observations has much, much broader implications. And we realized that, more than 20 years ago when I was coming off the Voyager missions to the planets Uranus and Neptune. I had started using the Hubble Space Telescope to do more observations of planets. And I was looking around going, what is the next big thing? What am I going to be able to do? And I heard about this next generation space telescope and said, you know what? That tool will be very important for planetary science. And so that's why I got involved in that mission, however many decades ago it was, right, Mark? It was a long time ago. Because I knew that in addition to the in situ spacecraft that NASA, ESA, and other countries send throughout the solar system, there are many places we cannot send spacecraft. There's like too many asteroids. There's the Kuiper belt is too far. We haven't been back to Uranus and Neptune for more than 30 years. So you need a telescope to do that. And Webb is so powerful that it will make really significant contributions. And then, of course, the whole question of planets around other stars, I mean, that they were just a twinkle in our eyes when we started working on this project. And now we have people like Hannah who are like, all right, ready to do it, ready to make the observations.
So we'll come back to some of the restrictions. I mean, if JWST is enormously powerful in its solar system observations, there are some things it will never see, as I mentioned in the intro. We're never going to look at Venus or Mercury. We'll come back to the technical reasons for that. But Hannah, what about your story? I've said it twice today, and I'll probably make myself look foolish by saying again, you're a bit younger than me and than Heidi. So this mission was already on its way before you started your PhD. I had been involved for 10 years before you started your PhD. So, but the exoplanet field is young as well, and it's changed dramatically over the years. So how come this observatory is actually even capable of looking at these things? I mean, it goes to what Heidi was saying. You know, we built a tool, but who ever saw that it would have anything to do with exoplanets?
Well, I mean, I actually, when going into my PhD, was anticipating the launch of JWST in around 2014. Of course, that didn't happen. And I'm now actually in the position where I have PhD students who are going to be able to work on the data themselves. So it's been a journey for me as well over the last more than a decade now. So I feel like I've been part of this journey as well. I came in, later than you guys, but from the beginning, it's been about preparing for this telescope and getting the tools together to be able to utilize data from this humongous observatory that is going to really change how we are able to view the universe, including exoplanets. And my task during my PhD was actually to learn how we can best use Hubble, the Hubble Space Telescope, to look at exoplanet atmospheres and develop the most efficient tools to do so. And a lot of that is going to be applied straight to the web science as well, and the instruments that we're using. So it all kind of adds up towards that journey. And a lot of it is investigating the planets that have been discovered. So the James Webb Space Telescope isn't going to necessarily be a discovery mission for planets. It's not going to go out and look at hundreds of thousands of stars trying to find planets. There are lots of other missions and telescopes on the ground that do that part for us. The really key part of Webb is that it's going to characterize the atmospheres of planets that have already been discovered. And it's going to do that primarily through the transit method. So we're looking at planets as they pass in front of their star from our point of view, and the light shines through their atmosphere, which then gets imprinted with information of what the atmosphere is made of. So we're going to be looking at, in the first year alone, over 100 exoplanets to try and understand what their atmosphere is made of. And in many of those cases, looking at parts of their spectrum, looking at different things in their atmosphere for the very first time. And these are things that we've been planning for and predicting for the last decade, and we're going to see if we were right or not. So when we talk about those exoplanets, effectively, they stay as points of light. We'll never actually kind of get an image with JWST. It's not big enough for that. But Heidi, that's exactly what's possible in our own solar system. So talk us through some of the kinds of observations Jupiter's so big from our perspective, whereas some of the other objects, Kuiper Belt objects, are point sources. So there's a whole range of different kinds of observations that can be done in our solar system. So talk us through a little bit of those.
Sure. Yeah, it's true. Jupiter is very large. Jupiter is very bright. And remember, we're using a telescope that was designed to observe some of the faintest objects in the universe. And so we have to be very careful and very thoughtful about how we use James Webb Space Telescope when we're looking at bright objects like Jupiter, like Mars, like Saturn. Nevertheless, there are clever tools we can use and strategies that we can use. Some of the kinds of the chemistry that Hannah was talking about on exoplanets, we're going to be doing some of the same kinds of measurements, not in transmitted light like you would see with an exoplanet, but in reflected sunlight for Jupiter and Saturn and the other giant planets in our solar system. And to sort of reflect back what you were saying, Mark, on that, we'll be able to do this across the disk. So we'll be able, for example, there's a team led by Imke de Pater and Thierry Fouché who are going to be looking at Jupiter and looking at mapping out chemistry in Jupiter's atmosphere, or pole to equator. We hope to be able to do that kind of work with Uranus and Neptune as well. So we can do this probing of the atmospheric chemistry, but in the case in our solar system, we can do spatially resolved work instead of just point source work for these large planets. Now, for objects like the Kuiper Belt, as you were saying, these are distant ice balls further than the orbit of Neptune, Pluto, and Pluto's 10,000 friends and relations out there in the Kuiper Belt. They are a key target for Webb in the solar system because they're hard to do from the ground because they're very far, they're distant, they're small, and so they're not resolved. They're point sources, and they're cold. And so Webb, which is designed to measure sort of the warmth from extremely cold things, is really well suited to do surface chemistry of Kuiper Belt objects and try to sort them out into the various classes that we know exist from their orbital characteristics. That's something we can measure of these point sources. They're different classes of orbits. Some are scattered, some are in a disk, some are, kind of stretched out in oval. And by tying the surface chemistry of these different classes to the orbital classes themselves, we are going to try to tease out the story of the formation of our solar system, which is written in that chemical signature, which we just don't have access to yet. And so Webb is going to be really powerful for doing that. And there are multiple programs. All of the different science instrument teams are collaborating so that we are not trying to duplicate one another. We threw all of our Kuiper Belt object science into one pot. We're collaborating on who is observing what, making sure it's all available to each other. Plus, there are people from our broader community who have proposed to do a variety of Kuiper Belt object science, including one of the large proposals, much time going to a team who are going to be looking at many dozens of Kuiper Belt objects to try to build up this catalog, this library of chemistry to help us understand the formation of the solar system.
And I wondered if I could just interject just something really quickly, just about the concept of booking time. So presumably anyone who's ever lived in a house with housemates or whatever else, just like you share resources on that. So effectively, how does that actually work? Because you would have thought that everything is already pre-planned, just like that the next few years, but it doesn't sound like that's the case at all. That actually people almost, would it be right to say they lobby, they propose, that they push for certain research to happen? Because I've never really been clear on how that works.
So it isn't really a question of lobbying. There's a couple of different ways that time is allocated on this telescope. Folks like Mark and I, who have specific science roles with the project, the instrument teams, we have some guaranteed time that was granted to us 20 years ago when we first started working on this project. And so we have a suite of observations that we've said for a long time, this is the kind of science we plan to do. And when we got close enough to the launch date, we got very specific, saying, these are the objects, this is how much time, this is what our guaranteed time is going to be used for. And then after that was clear and defined, then there's an open call that goes out to the world saying, do you want to use James Webb Space Telescope? If so, you write a proposal telling us what science you plan to do. And those proposals are all sent into the Space Telescope Science Institute in Baltimore, Maryland, and they evaluate all of them, and they are sent to teams of experts in the various fields, experts in cosmology, experts in galaxies, experts in exoplanets, experts in solar system, and they evaluate the proposals. And I want to mention that they do this in what we call a dual anonymous way. And these proposals are written so that you don't know who is proposing. You only know what the science is that they are proposing. Their names are stripped away. They're written in an anonymous fashion. They don't say, I plan to do X. They say, the science of X is this, and the team plans to do that. And that way you remove a lot of bias that human beings have when they're evaluating these proposals. So they spend a lot of time reading them all, ranking them all. This is top science, got to do with Webb. At the bottom, yeah, you don't even need Webb to do that science, so we're not going to. And then the stuff in the middle, there's a lot of debate and discussion about the merits of the science and the need to use Webb. And then, they pick as much science as they can fit in for that first year. And so that is how it is selected. It's a very competitive process. I think well over 1,000 proposals were received, several hundred were selected. And every year is another opportunity. So if you weren't successful this year, next year, try again and do a better job justifying the science that you want to do. Mark, did you want to add anything to that?
Yeah, I was just going to hand it over to Hannah, actually, because you've had to write proposals more recently. You're involved, I think, in a guaranteed time observing team, but also in what's called an early release science team. And the early release science is something which kind of falls in between the guaranteed time observers and what we call the general observers. So the ERS was designed to put science programs up front for the community to jump in, but all of those data go free to air immediately they're taken. So the teams that propose them, they'll be prepared to look at them, but everybody else can look at them, and that will help teams learn how other teams, what do JWST data look like? How am I going to approach it? How can I then write a proposal for the next round? So Hannah, how did that process work with the ERS team, and how did it feel when it was successful?
Yeah, I mean, I'm insanely lucky that I am part of leadership in GTO programs, ERS programs, and GEO programs. So I get a little bit of everything in the first year of observations. But the ERS is a really special one. It is designed so that groups of the community come together and say, we are going to do this science, and all of the things that we're going to do, how we're going to analyze the data, how we're going to produce that science, the different methods and tools that we use are all going to be open to the community. So we are a service to the rest of the community to lower that barrier of entry. So the data coming from this telescope is complex. It's state of the art in every single way. And analyzing that takes a lot of time. And we're trying to make it so that as a community with all of this experience and all of these new people coming in every single year, we're creating these tools that everybody can use, so that the focus is on the science. The focus of people's proposals that they put in can be focused around, this is an object that I want to understand for this scientific reason. And the barrier of going, well, actually, I don't know how to analyze this data is really very much lowered. So the goal of our ERS program, I'm part of the Transiting Exoplanet community program. We had over 100 people who were signed up as part of this program, active members of the program, is to create lots of different toolkits that can be used and are all open source. So anybody can use them and produce a kind of way, a description of how it is best to handle these data to get the results that we need to understand the objects we're looking at. So we will be taking data within the very first moments of its science operations. Transiting exoplanets are time specific. We have to look at the planet as it passes in front of its star. So we've got exact moments when we need to point the telescope at these targets. So we've got a rough idea when we're going to get that data down. And at the moment, we're working on the structure of how we're going to analyze that, what we're going to do, and how quickly can we get that information to the community so they can start getting ready for the next cycle, getting ready to analyze the data that's coming down.
Yeah, I think it's worth pointing out. I mean, Heidi said that the number of proposals was over 1,000. The oversubscription was, I hesitate to say only, but it was about 5-1 this time around, whereas Hubble typically runs at 10-1 or so. And I think that's partly because this machine is fearsomely complicated in a good way. I mean, there's so many different ways of taking data with JWST, spanning different wavelengths, doing spectroscopy or imaging, or putting little masks in front of stars and blocking the light of the star out and seeing what's around it, like an exoplanet. There's different ways of doing spectroscopy, some of which are very complicated and powerful. And I think there was, I wouldn't say there was hesitation, but there's exactly that thing that Hannah said. There's this big step that you have to take to be able to prepare a compelling proposal for JWST. So getting data out there from the outset, so people can say, well, okay, so they've looked at an exoplanet, or they've looked at a planet, they've looked at a star forming region or a galaxy. I now know the steps that were taken and what the data will look like. Hopefully that will increase the confidence. I mean, I don't doubt for a second that JWST will be massively oversubscribed. And 5 to 1, of course, meant that 80% of the people went away empty-handed. So they'll be coming back as well. But I think, maybe Heidi, maybe we could just dig in a little bit on that. So if we just take a simple object, a planet like, let's say, Mars or Jupiter, Uranus, pick Uranus or Neptune, the two that you have behind you there. How many different ways can you sort of cut and slice the light coming from it with the different instruments and the different wavelengths? So give us a bit of a feeling why you might want to take an image, why you want to take a spectrum, why near infrared, far infrared, or mid infrared, why they're complementary.
Sure. Let's talk about Uranus as an example. The Uranus atmosphere is a very complex atmosphere. It's gotten a bad rap over the year. People have said it's really uninteresting and boring. And that was because when Voyager flew by in 1986, it was, but it changed. And why did it change? And how is it changing? Those are the kinds of questions we're trying to find answers to. And it's hard because this planet, even though it's a pretty large planet, like 17 times the size of the Earth, it's really far away. It's close to the edge of our solar system. So in the sky, it is really tiny, and you need the most powerful telescopes on the ground and in space to resolve the disk. And so what is Webb adding that we haven't had before? We've used the Keck telescope at near infrared light. Keck is a 10-meter aperture telescope. It's huge, near infrared. We have amazing images of Uranus showing, equatorial waves and polar clouds and things like that, but it's only in the near infrared. And so Hubble has helped us by understanding the visible wavelengths, where we can see dark cloud features associated with bright spots in the infrared. You can't see the dark spots in the infrared. You can't see the companion clouds, so you need the two wavelengths to see this. Hubble has also given us ultraviolet images that have allowed us to probe the auroral observations of the planet Uranus. So Webb is going to add here is it is going to give us the infrared, the far infrared wavelengths that are very sensitive to the chemistry in the atmosphere, particularly the chemistry in the stratosphere, the higher levels in the atmosphere, whereas Keck and Hubble sense deeper in the troposphere. And trying to establish the linkages between the stratosphere and the troposphere, understanding what chemistry is actually happening, and is the chemistry we see that we have hints of from ground-based work, is that linked to the atmospheric dynamics that we can clearly see in the Hubble and the Keck images? We're going to try to tie all these things together with both spectroscopy, breaking the light out into its constituent colors, measuring the fingerprints of the molecules in that light, tie that to the disk resolved imaging that we can get with the 6.5-meter aperture of James Webb Space Telescope. So we can find chemistry as a function of location on the planet, and tie it all together with the other observations from Keck and from Gemini and from Hubble to get a comprehensive understanding of this planet that we, right now we have sort of pieces of the jigsaw puzzle. We have lots of pieces of the puzzle, but there's whole sections of the puzzle where we don't have the pieces yet. And so we can't build the picture. And Webb will help us fill in those pieces.
Okay. So let me just ask, let's get these technical questions out of the way then. Why can't JWST observe Venus and Mercury first? And second, planets were always there. They were always possible targets, but they weren't easy to do in the original design of the observatory. And you were a leader in trying to make it possible to look at planets. And people say, well, yeah, it's just there. It's standing out there. But there's something very different about the planets. So those two issues, talk us through those two technical aspects.
Sure. So those of you who have seen pictures of Webb, and you can see a little model behind me, and you know about the big sun shield we have. That sun shield is there to protect the telescope instruments from the warmth from the Earth and the sun and the moon. That's why the sun shield is there, is to keep our telescope in shade. But the problem is from out at L2, that sun shield is also blocking Mercury and Venus because they're close to the sun from where we're looking from L2. And we're never going to turn the telescope back because that just destroys the whole purpose of having this hyper cryogenically cold telescope. So we will always be looking away from the sun. And so we will never be able to look back towards the sun. We will not look at the moon. We will not look at Earth or Venus or Mercury. Near-Earth asteroids are an actually interesting case. These are asteroids that are in orbits that bring them close to Earth. And there are times when they are in certain positions in their orbits where we can get just far enough over to catch a glimpse of these near-Earth asteroids. So those are the closest things to the sun that we will be able to observe with Webb. So that's why we're never going to look at Mercury and Venus or the moon, which we have done some of these things with the Hubble Space Telescope because it doesn't have these constraints. It's not an infrared telescope. The question, though, of looking at other planetary objects like Jupiter or a Kuiper belt or Saturn, any of these other objects that are far enough away that they're in our field of view, the challenge is these objects move in the sky. And other objects, galaxies, most stars, they're more or less fixed. And I'm waving my hands a little bit because there are some stars that do move. Barnard's star moves. Gaia, that is all about finding the accurate positions of stars, and they move. But more or less, they're more or less fixed in the sky. And we use star trackers to find where we're pointing the telescope. But our planets move pretty rapidly. And so if you lock on stars and you take a picture, your planet or your asteroid or your comet will move through the field of view and smear it out. So you actually have to do what we call non-sidereal tracking. We have to not track at the star rate, but actually track with the motion of these objects. And Mark knows this story because we lived it together. When Webb was originally crafted, we have what we call level 1 requirements. These are science requirements that the mission must fulfill to be deemed successful. And in the very beginning, non-sidereal tracking, moving target tracking was a level 1 requirement. And one day we got an email with the updated level 1 requirements and it was gone. No moving target tracking. I'm like, what's happening? Never got an answer. I don't know who it was that made the choice. No one consulted us, the science working group. They just said, moving targets. Nah, we don't need that for galaxies. Boom, it's gone. And then we spent years advocating, working to get it back, to demonstrating that it's not impossible. Hubble does it, the Fuse Space Telescope does it, Chandra does it, every telescope does it. In the end, it was restored. There was some funding provided by NASA's Planetary Science Division to help do some of the implementation of that. And we had to make the choice. People are like, what do you guys do? When you say Mark and Heidi, you've been working on this for 20 years. Like, what are the kinds of things that they had scientists for? Well, one of the kinds of questions is to say, okay, Heidi, you want moving target tracking? Tell us exactly what level of moving target tracking you want. How fast must it move and why? And so then you have to develop a justifiable science case saying, I need it to move 30 milliarc seconds per second over a 10-minute span. And I need to do that because that will allow me to do these observations of Mars most of the time. And it'll allow me to do every Kuiper belt object, and it'll allow me to do everything in between. And so you have to build the science case for that and justify. That's just one personal example of the kind of work that you do when you're working as a scientist for this team, for a team like James Webb Space Telescope. So I think I answered your two questions.
Yeah, I mean, it's that business that we lock onto a star, and of course, if you're looking at another star nearby, you don't have to do anything. But when you're looking at that planet, you have to be able to move that star across that field of the guider, and that was non-trivial. It wasn't just a matter of changing some kind of motor or some kind of rate. You had to implement software which would then allow the tracking star effectively to move across the detector but still be picked up. That's one of the Canadian contributions to this international mission. So Alex, let me hand to you.
Yeah, just a welcome to everyone that's joining us from all over the place. We have people watching from Canada, from Ireland, the list goes on and on. And one of them, Grant Blair, has a really good question for Heidi. I was just reminded as I was just sort of staring at the well-known gas giant of Bespin from the popular science documentary, The Empire Strikes Back. Heidi, Grant Blair wants to know, so what might we expect from the JWST to add to our knowledge of Jupiter that we haven't already been able to determine from existing scopes and probes? So I guess it's almost like, what don't we know? What are we hoping to learn?
Well, anytime you're opening up a different wavelength regime like the infrared with the kind of sensitivity and spectral resolution we have with James Webb Space Telescope, you will learn new things. To give you an example, in the case of Jupiter, you might not know this, but there's a red spot, right? We still don't know what the chromophore is that makes it red. I mean, after all these years. So one of the targets that my team will be studying at Jupiter will be doing very high resolution spectroscopy of the Great Red Spot. This is work led by Lee Fletcher at University of Leicester. They're going to do very high resolution spectroscopy of the Great Red Spot. Can we figure out what the chemistry is that's causing the red color? I mean, okay, that's cool. There's, of course, a wealth of, that's sort of a wow thing. There's many other detailed questions about the chemistry and about the circulation around the Great Red Spot and how the different chemistry, the chemistry of the different regions interacts with one another, and how does the dynamics change? Lee and his team will be probing all of those kinds of questions. And as I mentioned before, when we were talking about different altitudes in the atmosphere, we will be able to have different sensing of different altitudes with Webb than we can with other telescopes and other missions to compare. Let me give you an example of what I think is going to be very powerful. You may recently have seen some really gorgeous sets of images of Jupiter taken with Gemini in the near infrared, Hubble in the visible, and then observations from the Juno spacecraft, which is in orbit around Jupiter, that is doing microwave sounding of deep levels of the atmosphere. When we add Webb to that triad so that we have 4 objects, Webb will sense even higher than the Gemini Observatory has been able to sense with its telescope. So we will have multiple probes of the same parts of the atmosphere simultaneously, if we're clever about our scheduling, to give us a much more holistic understanding of the atmosphere all at one time. That's important for very dynamic planets like Jupiter or Saturn or Uranus and Neptune. You can't take observations made in 1994 and compare them with observations made in 2022. The planet has changed. So to truly understand, you need this simultaneous suite of observations. So that's one of the kinds of things that we're going to be doing with our Jupiter observations with Webb.
So we'll come back to 1994 because I don't think you chose that as that wasn't by chance you chose that year and Jupiter, as many people may remember. But Hannah, let's hand to you because of course, if you were to believe the newspapers, the less studied journalists, the only thing that's interesting about exoplanets is to find a planet that's like Earth, that's got an atmosphere like Earth, and it's got aliens. Of course, some people out there in the community think that it's always aliens, and we found aliens anyway. But exoplanets, there's a much more diverse story there. And in fact, we may not even be able to get to that point of an unambiguous detection of a habitable or inhabited planet with JWST. But what else is interesting about exoplanets that we don't know after, 25 years of study?
Yeah, humans are inherently egocentric. So we're, of course, like, oh my God, we must find aliens. That's nowhere near the point of this. Like, there's so much stuff that we need to learn along the way that since the discovery of exoplanets, it's basically been shock after shock after shock. The first planets that were discovered around main sequence stars, similar to our sun, were these giant Jupiter-sized worlds, but they were so close to their star. They were 20 times closer than we are to the sun, even closer than Mercury is, tidally locked with a permanent day side and a permanent night side. These giant gas planets very close to their star where they couldn't have formed. So that actually allowed us to rewrite the entire history of our solar system and how it formed and what happened to Jupiter and Neptune and Uranus very early on in the formation of our solar system. And the next big shocker when the Kepler mission, which was launched in 2009, was searching for planets. This was a discovery mission. It was looking for planets around other stars. It actually discovered that the most abundant type of planet in our galaxy are planets that are slightly bigger than the Earth, but smaller than Uranus and Neptune, something that we have absolutely no representation of in our solar system. So again, there's this humongous number of planets out there that we never even imagined or thought of. And it just keeps getting more and more surprises as we learn more about exoplanets. And of course, just like Heidi's been saying, it's so important that we've got these other telescopes that we're working together with what we're going to learn from Webb. The Hubble Space Telescope is not ending. We're still going to be using it to learn about the UV atmospheres, the optical atmospheres of these planets, to try and understand how it all connects together. An atmosphere, as we know from our own, is incredibly dynamic. And there's lots of different small changes that can then affect what we're able to measure, what we're able to see. But the James Webb Space Telescope is going to reveal to us this whole new wavelength range in the infrared. And the really cool thing about this wavelength range is this is where all the carbon species pop up. So CO, CO2, carbon dioxide, methane, they all have these fingerprints in the infrared that we haven't been able to measure before. And by comparing those measurements to measurements of things like water vapor in that atmosphere, we can get an idea of the balance of different materials in those atmospheres. And the balance of those materials is actually really important for us to understand what's going on inside these planets. We're looking at, for exoplanets, very high up in their atmospheres. So we need to use that information to learn what's going on down deeper. And a lot of that is to do with the balance of these chemicals. But one of my favorite things that we're going to learn about these atmospheres, and this is one of the things that I worked on very early in my PhD, is understanding the clouds in the atmospheres. I said that these planets are very close to their star. That makes them very, very hot. So their clouds aren't made of water vapor, water droplets like we have here on Earth. They're actually made of rocks. So the rocks that we're standing on, the sand on our beaches is actually forming clouds in the atmosphere. And when you melt that sand down, you actually form glass. So the clouds in these atmospheres are tiny little droplets of molten glass and iron and rubies and sapphires. And we need to understand what they're like. And this is the only way we can do it with the James Webb Space Telescope. So it's got these amazing things that we still are trying to learn. But to bring it back to that egocentric thing, you can't know anything about these planets that we've got right now. When you read these planets that have been discovered in the media, they're drawing conclusions about habitable nature from just a size. They just know the radius of the planet. But that's not enough. You also have to know the mass of it, get an idea about its density. What is this world's density like? But then fundamentally, you have to know about its atmosphere. We have 3 perfect examples in our solar system: Venus, Earth, and Mars. If we measured those as exoplanets, you would see them in the media as being all Earth-like. And we know that would be wrong. So we need to measure their atmospheres to understand that. And James Webb's actually going to take the first steps in measuring the atmospheres of these worlds that we've discovered that are roughly the size of what we think should be rocky. But we don't know what their atmospheres are like, and we're going to make some really great steps towards trying to understand those. So it's the next step in the game. Hubble started us off by going, do these have an atmosphere? Okay, well, we need to look a little bit closer. We know they don't have big hydrogen atmospheres around them like Uranus and Neptune. So what's the next step? How can we push it further? And the sheer size and spectral resolution of James Webb is going to allow us to take that next bold step.
Let me jump in here, though, because I want Hannah, you to talk a little bit about the fact that most of the ones that we're really going to be digging into with Webb are probably not going to be around sun-like stars, right? They're really more going to be around these M-dwarf stars, these cooler stars. Maybe you could talk a little bit about what that means and the TRAPPIST-1 system, which is like on everybody's list, and why is that on everybody's list? Go ahead.
Yeah, so you've hit on it right there. So our star is a very particular size and temperature of star. It's a really kind of temperate, middle of the road star in terms of all the stars that we have in our universe. But the most abundant, the most common type of star are these M stars. These are small red stars, and they're small and they're red because they're colder. Now, if you make your star colder, for your planet, like our planet, to be this temperature, a nice room temperature of over 25 degrees, let's say, let's try and keep it there. If you want it to be that temperature, you have to get closer to that star because it's so much colder. So you have to step closer to the fire to keep warm. And that means that some of these planets around these very, very small stars, for them to be in what is termed this temperate zone, this habitable zone, the Goldilocks region where liquid water can exist, they have to be much, much closer in. And in some cases, they're orbiting around their star, their year is just over a week. So they're incredibly different places to what we imagine. And we still are trying to understand, but if your orbit is just around a week, you actually might be tidally locked. Those rocky worlds might have a permanent day side and a permanent night side. And that changes things like the dynamics of the atmosphere, but it also changes what you can imagine as life on those. And we see it in sci-fi all the time, these kind of dichotomous worlds where you've got the
Terminator life, right?
Exactly. this ring around them. And it's really fascinating to think about in that kind of more theoretical and imaginative way. And I find that's a really helpful way to kind of start the process of asking the right questions of what's the temperature like? What does that mean? How far away is it? How does the star's radiation change? So these M stars, they actually put out more heat in the infrared part. Their light is infrared. So what does that change to the way that any kind of vegetation might affect it? So there's tons of really theoretical questions, but James Webb's actually going to be looking at these planetary atmospheres, and we're not going to get anywhere near the answer to those questions. The first thing that James Webb's going to answer for us is there carbon dioxide in these atmospheres? That's the main question we're going after for these planets, is we're trying to understand the amount of carbon dioxide in their atmospheres, because that's a spectral signature that's really strong. And James Webb has the perfect instruments to measure that. So the biggest question, I'm on a large program for GEO, which is led by Natasha Batalha and Johanna Teskey. And that program is looking at 11 small planets around these cooler stars. And the biggest question we have, do they have an atmosphere at all? We genuinely don't know. We're going to learn so much.
So many questions. I wondered if I could just interject one from the audience. Another one's come up, and it actually it pertains to something that was said earlier, perhaps when there was a brief mention of NEOs. And Grant has asked an interesting one. Basically, will JWST have the ability to temporarily be redirected at very short notice in order to use its unique abilities to image any transient phenomenon? I guess it's something that's been in the news, relatively recently, and so on. And so, what's its agility? How quickly could we adapt given new information?
So we can look at things with a moderately quick turnaround. Typically, command sequences are uploaded every 2 weeks, and so that's kind of a time scale that we think of typically. There are things called disruptive target of opportunity. Target of opportunity means a thing has happened that you haven't predicted, but you think it's so scientifically important that you want to break in to do it. But it might happen, right? That's why you've written a proposal. And things like, if another interstellar object comes by, that could possibly be a disruptive target of opportunity, because you might want to break in and try to get on it right away to get a spectrum of it, for example, or if it gets close enough, get images of it. So the challenge is that the way this telescope is designed is it is designed to try to be very conservative about slewing around the sky. We don't want to go from here to here. And so it's designed to go from here to here to here to here to here to here. And they craft their programs to try to minimize that kind of motion, right, as we are moving around. So it's a balance between where these objects are in the sky, these objects that you might want to interrupt for, and how important are they, and how often are things sent up to the spacecraft. I would be surprised if we had a super short turnaround. When we've done things like, I'm trying to imagine, I think with the Hubble Space Telescope, one of the shortest turnarounds that I'm aware of is when in 2009, when a second object crashed into Jupiter, not Shoemaker-Levy 9, but a later one, where we were able to get on sky within 3 days, really quickly. But that was unusual, and it was really challenging and difficult. I'm thinking more like a week, but I don't know. If a supernova went off, I'm sure supernova went off in a nearby part of the galaxy. I'm sure every effort would be made to see if we could get on it right away. Mark, you want to add anything to that?
Yeah. You're absolutely right. I mean, the reason it can't be moved very quickly is that it's a big floppy telescope. I mean, if you think about Hubble, it's a rigid tube and it's got a mirror and it's got its instruments all bolted to it. The way that JWST is built with this giant sun shield and this big mirror out in the open, it's relatively floppy. I mean, I don't mean to say it's sort of wobbling around, but if you change its orientation dramatically, you change the angle with respect to the sun, and you can change the thermal load on it. Even though you've got the sun shield in place, the thermal load on the other side changes, and the telescope might sort of slightly change its shape. And so we want to minimize those big slews because we want to minimize those temperature changes on the telescope. The other thing which is important about these kind of targets of opportunity is to remember that because, as we kind of talked about, you can't look towards the sun, you can't actually look directly opposite the sun either at any given time with JWST. If you imagine the sun, the Earth, JWST at L2, the telescope is here and it can point around at 90 degrees to that line by spinning around, but it can't look that way directly out. So at any given time, it can look at a roughly 35% of the sky. And over the full year, as the telescope moves around with Earth around the solar system, around the sun, it can see the whole sky. But imagine there's we see something heading towards Jupiter and it's in the wrong part of the sky at the wrong time. There's nothing we can do about that. We won't be able to just say, well, let's just change things and let's have a look at Jupiter. And that's not just when it's on the other side of the sun, where you obviously couldn't look at it, but even if it was straight out, staring you in the face, and everybody from Earth can look at it, you couldn't look at it with JWST.
And let's just, this isn't just about JWST. This is true for ground-based telescopes too. If your supernova is in the northern hemisphere, you're not going to use telescopes in Chile to look at it, right?
Yeah.
They're just limited. These telescopes, they have parts of the sky that they can look at. And so, sometimes we're lucky, sometimes we're not.
So one of the things I wanted to bring up, if we kind of move on a little bit in the remaining few minutes, is just sort of talk more broadly. And the one thing I was thinking about, I was talking to Hannah earlier on today doing a recording for her podcast, Exocast. And then I went out cycling. It's freezing out here, and I just needed something to keep my brain going. So I was trying to work out, when did we first meet, Heidi? And I think we probably met in person when we first got involved in JWST. But we may have crossed over earlier because you were a PhD student in Hawaii and I spent a lot of time on Mauna Kea in the 1980s. So we may have been, close by. And then there was the other time where we didn't meet, but we were both looking at the same thing. And that was comet Shoemaker-Levy 9 in 1994. This comet that broke into lots of fragments and they pinged into Jupiter one after the other over a series of days. And these enormous plumes came out. We saw them from the Calar Alto Observatory in southern Spain, these giant plumes, which I think probably people didn't expect. And then you were using Hubble at that time. And so talk us through what that was like, because, we were both relatively young at the time. This was a huge thing that kind of came out of nowhere.
That's right. 1994. The story started in 1993 with the discovery of Shoemaker-Levy 9. And I remember when a graduate student came running down the hall, it's like, have you heard a comet's going to hit Jupiter? And I'm like, yeah, so what? Comets are small, Jupiter's big, but it's actually not quite correct to say that some people we didn't know about those giant plumes. There were people who actually had done modeling of very large explosions And they actually cornered me at an AGU meeting, American Geophysical Union meeting, where I was talking about the observations we were going to make with Hubble of this. And they're like, Heidi, you got to look for these plumes. They're going to be so huge. They're going to stick out beyond the edge of Jupiter. The impacts were on the far side of Jupiter, so we couldn't actually see from Earth, couldn't see the impact sites, but the plumes were in the end, they were so tall that they peaked out beyond the edge of Jupiter, and we were able to image them with the Hubble Space Telescope. And, there was this linkage, Mark, between us, because we were at the Institute. We had already uploaded all of our observational plans to Hubble, and it was happening, it was going on. And we were just sitting there waiting, kind of, going like this on the desk, like, what's happening? And we heard about your guys' observations from Colorado of an infrared flare of some, and we're like, oh my gosh, something's going to happen. And then when our images came in, we did actually in the first set see the plume top sticking out, which was astonishing. And then our second set of images, we saw these big black spots on Jupiter, which was just mind-blowing. Not at all what I had anticipated or expected. And what I learned is that you can make all the predictions you want, but sometimes it's fun to be completely wrong. And this was one of those cases. Just to tie this back to JWST, we have subsequently seen more than half a dozen impacts on Jupiter. The amateur astronomy community is the leader in this because they watch Jupiter all the time. And when they see an impact, when they see a flash in the atmosphere, like which is a bolide or a super meteor, we now know whether or not we need to turn Hubble, Gemini, or in this case, Webb to Jupiter, because we've now calibrated these flashes that are seen on Jupiter's atmosphere. We know now sometimes they're not big enough to make impact sites on the planet. But if one does happen while Webb is up and operational, there is a target of opportunity proposal already written, ready to go to target Jupiter if Jupiter is in the right part of the sky. So the teams are ready. So yeah, Mark, that was a long time ago. That actually wasn't why I picked 1994.
Oh, okay.
Because I picked 94 because that was also the year, that was July, Shoemaker Levy 9, but November of 94 was my first actual real scheduled observations with Hubble of the planet Neptune. And where I was hoping to study that great dark spot on Neptune that Voyager had discovered, but it had disappeared by that time within just 5 years. And so that's the whole cottage industry of trying to understand Neptune's dynamic spots. They come, they go. Sometimes there's two, sometimes there's one. Why is that? We don't know. Webb is going to help us understand that.
Right. So I can't leave this be because I remember first going to Mauna Kea as a student, and we were using the United Kingdom Infrared Telescope. But the other sort of famous infrared telescope there is the Infrared Telescope Facility, IRTF, built by NASA to actually do ground-based observations with Voyager on the flybys, but of course used for many other things. And I remember a lot of time was spent looking at Jupiter in the 80s and 90s. And I remember one of the support scientists who shall remain nameless, his epithet was, nothing could be stupider than looking up at Jupiter, because they had spent so much time looking at Jupiter for years and years. But
that turned out to be really important, I will say.
It did. And I think
because we've been able to understand now, climate variability on Jupiter over decadal timescales and actually see changes, patterns that occur on Jupiter's atmosphere. And you have to have decades worth of observations to do that.
Yeah,
so,
and even the Great Red Spot disappearing, right? I mean, it'll be gone at some point, and
not anytime soon. I just want to make sure.
Well, yeah, get your observations done now. Come on, hurry up.
Well, I mean, I just want to jump in there really quickly. One of the things that ceaselessly impresses me about this mission in particular is the time scale. From concept to deployment, and what we're seeing now is the bloom of something that was planted many years ago. Chris Lee pipes in from the audience and asks Mark, is the science that you wanted to do 20 years ago still even needed?
Yeah, that's a great question. And I answered that when we were talking to Hannah earlier today. I am doing pretty much the same observations in my guaranteed time observing that I said I would do 20 years ago. And that's because JWST is not just incremental. it's a telescope. We have telescopes bigger than 6.5 meters on the ground. You can get some diffraction limited images, so the sharpest possible images using laser guide stars, but JWST will get that hopefully in a few weeks' time or a couple of months' time when it's all lined up. So you get sharp images, but it's because it's cold. It's because it's able to reduce its own emission down to such low levels that we're actually limited just by the glow of our own solar system, the zodiacal light. And that's just not true on the Earth. The sky is glowing, the telescope's glowing, the upper atmosphere at 80 kilometers is ablaze with light in the near infrared. And so the level of extra sensitivity we get with this cold, large telescope is so large, it's such an incredible step forward. Nobody has been able to touch the stuff between what we can do on the ground and what JWST will do. I mean, slowly, incrementally moving down at the edge, but we're talking factors of hundreds or even thousands more sensitive at certain wavelengths. And so that science still exists. The stuff we said we were going to do 25, 30 years ago. And that's true of the extragalactic objects, of course, the things we've not talked about at all this evening, these high redshift galaxies, which are so close to the beginning of time, so far away from us, so far stretched. All of their light is in the infrared, and you just can't do that stuff from the ground. Hubble can do a little bit of it, but not far enough. So those science goals are untouched. What's brilliant about JWST, though, is that this multi-mode, complicated observatory is able to do many things we didn't even dream of, and exoplanets are part of that. But So Hannah asked me earlier today, what's the most exciting thing you think you'll find with JWST? And it's trite, but the most exciting thing we'll find is the thing we don't even know about yet, because this machine completely changes the paradigm of sensitivity and resolution. We're not going to find aliens sort of looking at things in a kind of completely odd way. It'll be things we know. There are galaxies, there are stars, there are planets, those kind of phenomena, but how they work, there's lots of unanswered questions, and JWST may pick up something. Some young graduate student now just starting their work will see what we're doing now, and in 3 years' time they'll write a telescope proposal, they'll get the observing time, and they'll find something we never even thought of.
Well said. I agree. Everything you said.
Indeed. Well, I mean, it's certainly an exciting moment. If I could just sort of, ask collectively as we sort of, dwindle down, what next? It's been a big week. It's been a big few weeks and so on. What can we expect in the coming weeks, months, and years? Because, of course, this is a story that it's not going to go away, and rightly so. We're just at the starting blocks.
Well, let me just pick up on that first. In the near term, in the next few weeks, you can expect intense tedium, unless you're Marshall Perrin and the people who are actually going to be lining the observatory up, because that's what happens now. We're on the edge now of getting light onto the detectors, but any star we look at today will be split into 18 stars because we have 18 segments which are not lined up. And that process of getting them lined up to bring all the starlight into one point and then adjusting the distances between the mirrors so that they're not only collecting all the light in a place, but effectively interfering to form the sharpest possible image, it's going to take several months of really hard work. But it's that's definitely a paint drying thing, watching that kind of process go on. But vital. If we don't get all of that, we don't get all of the wonderful sensitivity that we built this observatory for. But I'll hand up for the science. Heidi and Hannah are best qualified.
I just want to add on to that. This process of aligning the mirrors, and we use the analogy grass growing. You can watch the grass grow. That's the speed at which the mirrors move, and there's a lot of them. So it will take a long time to do that. Even after that is all done, we have a perfectly aligned mirror for the near infrared camera. We then need to align all the other instruments as well. And so that's another couple of weeks or a month. And then we need to make sure that all the different modes that we have been talking about, transit mode, coronography mode, a spectroscopic mode, direct imaging mode, integral field unit, we have to make sure all of those different modes are working properly. And that part of commissioning, that is another several months. And so that is why we're saying, not until June do we expect to see the first images, the first data coming out of here. And what those first images are is super top secret. I don't know. Mark doesn't know. Hannah doesn't. None of us know what that is going to be. But there will probably be several of them that will be done by the teams, the instrument teams who are doing this commissioning work. And we will expect to see those in June. And then these early release programs like the one that Hannah's involved in, and there's 13 of them in different kinds of fields of astronomy. So all different kinds of fields of astronomy will get hands-on data right away. That will then start to come, and then the rest of the science will start to flow. So it is going to be a long process. I know NASA will be sending out periodic updates when certain milestones are achieved. It's not going to be quite as rapid as it was during the past month when things were unfolding and it was all happening in real time. So you have to have a little bit more patience. But you know, people like Mark and I have been waiting 20 years, so we can wait a few more months.
Yeah. I mean, I think the one thing to put it in context for you, Hannah, I mean, one thing which we know now about JWST is that the perfect delivery by the Ariane 5 on its trajectory and the mid-course burns, which have now just yesterday or earlier this week put it in this orbit around the L2 point, 1.5 million kilometers away, we know that we have enough fuel for the mission to be much longer than we originally planned. Now, there may be other things that fail, but fuel-wise, we should have a much longer mission. Now, that's beyond my retirement. It's beyond what I'm thinking about. But for the you know, the community which is here today, the younger people, you've got a much longer perspective now, perhaps, than you thought you had before. And of course, there are other missions to come afterwards. So I wonder if you could kind of give us a bit of a walk through what people in your generation are thinking about what comes next. I mean, we've done our bit, Heidi and I. I mean, pretty much. You know, we've built you this observatory, or at least the people that we've
here
worked
it is.
You know, go for it. But you've got to build the next one now.
I mean, I'm just thinking about all of the students that are going to get to use these data sets. So, I mean, we have students right now, we've got undergrads right now who are going to be able to see the first data coming down from Webb and actually get their hands on that. And then we've got, 20 years of this? That's generations and generations. And something Mark said earlier, there might be somebody who isn't even born yet that gets to play with Webb data. Like, isn't that just amazing? We've got this humongous time to use this really diverse observatory, and that's one of the key things. Is this is a hugely diverse observatory. We are going to be measuring things from the first ever stars forming in our entire universe to the planets right next door to us, and every step in between, the formation of galaxies, the formation of stars, the formation of planets, down to what's the nature of these planets' atmospheres, what can we imagine these worlds are actually like, to understanding the formation of our own solar system through the Kuiper Belt and through our giant planets. That breadth of science that we can do puts this massive roadmap in front of us for the next 20 years. And it allows us to use those unknowns, use those new things that we're going to learn in that time to build the next observatory that can go after more and more and more. So we can really put ourselves, our planet, in that galactic, in that universal context that we as scientists are really excited about. It's just building these blocks and as Heidi said, finding those puzzle pieces. The puzzle's just much bigger than we think it is. And, you know, I'm working on this little bit of it. Heidi's working on this little bit of it. Mark's kind of going, oh, but what about this bit? And how do they link together? And it's all about bringing that. So I'm excited for all of the students and all of the future scientists that are going to come from this mission and its data.
And I just want to add too that, you know, this whole period of time that Mark and I have been working to help build this telescope for this new generation that is now going to be able to take advantage of it, we were busy using the existing telescopes, you know, Webb and Keck and Gemini and all these other ones, VLT. Hubble, yeah. Did I say Webb? I meant Hubble. Yeah. They're all together in my head. But I just want to share, Hannah, to you, all the Hannahs out there and all the young people coming up. You know, now is the time for you to be using this and also working to be building that next generation space telescope, the next great observatory. When I talk about great observatories with a capital G and a capital O, that's a telescope that can do this breadth of science exactly as you articulated, Hannah. And to really to make that next quantum leap, to be able to actually measure dozens of Earth-like planets around sun-like stars. That's not something that's within the grasp of Webb, but it will be within the grasp of a next great observatory that we collectively are beginning to envision for the next generation to build.
And I think it's important that that next generation isn't just limited to ESA, NASA, CISA. This is an international thing. These are things that are getting bigger and bigger, and it requires effort from absolutely everybody. This is a really, really wonderful international telescope. And so was Hubble and a number of other different missions as well. And it's so important to have that aspect of just huge collaboration across the planet.
It's wonderful when humanity works together to do great things. I think, Alex, I think one reason a lot of people have been kind of joyful about Webb is that it's a positive thing that multiple nations have gotten together to do and move forward. I think it's a wonderful example for how we as a species can work collectively together to do great things.
Indeed, I fully agree there and echo your sentiment. I think one of the most resounding lessons that we've had, I think, in the course of doing Space Rocks Uplink, for instance, and all these conversations, is that there are far greater lessons than merely the discoveries that this research represents. It's what it means about cooperation and what we're capable of. And certainly in these dark times, one in which Uplink was born, in the absence of our ability to actually do proper physical events, it's really been quite the beacon. So I'm sure I speak for Mark when I say it's such a pleasure to be back doing Uplink, and it's been such a pleasure to have you both. And now we're going to have to do a really cheesy thing, but I think we're Mark, we're kind of talking about Gene Roddenberry anyway, in some sense, aren't we? Or certainly a vision of what humans can be like, perhaps, which involves a hand sign, which we always do. And Heidi and Hannah, I'm so sorry, but you're just not exempt. You have to do this with us now. I hope Mark warned you.
Not at all, but yeah, no, exactly. I mean, Star Trek is the one that we tend to follow here a little bit, because it is that positive look on the way that we might progress. We know of other science fiction where maybe it isn't quite as positive and a bit more dystopian. That seems to be the world. So, of course, it's this hand sign, which is live long and prosper for space, and this one for the music that we love, of course, the rocks symbol. We didn't get to talk to you this evening, Heidi, about you being a deadhead, and we didn't put Hannah on the spot for her best gig that she's ever been to. But we'll come back to that. We will have opportunities in the future to talk to you both, I hope, whether it be this way, on Uplink, via Zoom, or hopefully, for all that we've been a family for 20 years, Heidi, I haven't seen you for a good 2 years, and there was that moment where I thought I'd be in Baltimore for the launch, but I'm sorry, unfortunately I had to go to Kourou instead and see it there. But yes, and nothing will make me happier than to see the JWST family together. And it's huge. It's not just the 20 of us; it's the tens of thousands of people that have made this possible. And it's emotional to think of what we've done so far and what's to come. And I think that's impressive. So we'd love to talk to you again, maybe at a live event when we go back out on stage and do it that way.
Fun. Thank you so much for the opportunity to share.
Yeah, it's been absolutely great. Thanks, guys.
Thanks very much. We'll see you soon. Bye-bye.
Bye-bye. Well, and there we are. Well, Mark, we're back in the saddle, so to speak. And wow, what a great way to kick off the year as well. Certainly the story of 2021 and 2022 and beyond, in many ways. This is the story of our times.
Yeah. Occasionally you get a bit locked into the things that you do and you lack perspective. And when I came back from French Guiana, seeing the launch, being surrounded by people who knew exactly what we were there for, exactly what that mission was, everybody celebrating what we had done, you lack that external context. But I was wearing this shirt, which is, the JWST primary mirror, the ESA logo. I walked through airports in French Guiana, in Paris, and at Amsterdam. And on each occasion, people stopped and pointed and said, "Oh, are you involved in that?" On the airplane getting on, people say, "Oh, look, the Webb telescope." And when you achieve that, when you go outside of your sphere and you realize that you've engaged other people, and not just in kind of the moment, but have the opportunity to talk to them about what this means, what we've done and where it's going, but the broader picture of what it means to come together, there was a real sense of warm enthusiasm from people that they had just seen something amazing happen. And that was before all of the other stuff, the deployments and so on. We've seen that in the people that have followed on social media and elsewhere. And I go back to what Heidi and Hannah said. That offers us a bit of hope, and what you said as well, right? This is not ultimately about the discoveries we make. That's interesting to us scientists. It's great for the encyclopedias. It's fantastic science. But it means so much more than that. This is just the very beginning of JWST, despite it having been 30 years old. In many ways, we've taken the next step and just started.
Indeed. Well, incredibly well said, Mark. I mean, I know I speak for a lot of people. I feel incredibly privileged to have a window in on it. And so thank you so much for all the work that you've done. If you don't follow Mark on Twitter and you're still watching, you've absolutely got to follow him. Some of his threads have been absolutely Twitter breaking, just a phenomenal insight into the day-to-day and what's been going on. Mark, a real pleasure to see you again. And we'll look forward to the next one. Just go to spacerocksofficial.com, sign up to our newsletter, and we'll have news about the next uplink very soon indeed.
All right. Thanks, Alex. Thanks, everybody else. See you soon.
Thanks, Mark. See ya.